By looking at what points? Yeah, we'll start by picking a potential f of x, right? And then what were the good values to look at? Look at what? Look at max and mins. See if they, and then what do we look? We see if they what? Correlate, right? Correlate. Correlate, yes. Exactly. See if they correlate. And also see if signs match up. What do I mean by signs match up? F increasing means what? F prime is greater than 0, right? So if the function is increasing, it means that the derivative better be above the x-axis. And there's only 6 possible combinations. Essentially, what's going on when you take the derivative of an integral?
Nothing.
Nothing, essentially, right?
Yeah.
But what's the key difference here? What's the one term in there that makes this a little different? The x cubed, right, exactly. So when you take the derivative of something and you're plugging in an x cubed, what do you also need to make sure you remember that is always in play?
X cubed.
Yes, but what rule does that kick off? There's a differentiation rule that you're always using, but it doesn't always show itself because you're usually multiplying by 1. The chain rule, exactly. So can someone tell me what g prime of x is going to be? Can someone tell me what it's going to be? Is it t? What's it going to be? What do you plug in for t? X cubed over 1 plus x cubed cubed times the derivative of what? Of x cubed. Yes. Usually when we do the, not usually, but many times when we do the chain rule, what are we taking the derivative of on the outside? What? Can you speak louder? Then it's just 1, exactly, x to the 9th. So it's times what? 3x squared, exactly, right. So g prime of x is equal to 3x to the 5th over the square root of 1 plus x to the 9th. Does that make sense, everybody?
But when you get to things
Yeah.
like
Pause. Okay, there's that. Now we're taking the derivative of that. Which one can we do directly the derivative of right now? The first part or the second part?
second part.
Yeah, so we know the derivative here is going to be, what's that going to turn into? Times 1, just to put that in there. That's d dx of what? I'll just put it in there just so you can, it's d dx of x, which is 1. Correct, okay. Now, Bill, what's the problem with this one? What's the problem? Because look at what look at what we have here. This is what the rule says. Look what the rule says. It's if it goes from A to C, you have to do it from A to B and B to C.
Will you see smaller than A?
We don't know. But right now, Shinsai, right now, this right here is the bottom one. This is the top one. Not always. What happens if it's a fraction? What's the square root of 1/2? What's the square root of 1/4? It's not always true, Bill. Making it what? Exactly. Very good. Making it negative. So you have negative of, to what? Root x of e to the t over t dt. Because we know that if you flip the limits of integration, what happens? That's it. Exactly. So now, can we actually do this? Yeah, so what's the derivative going to be? If we do the derivative, what's it going to be? Yeah, let me just write this in here. We're doing the derivative, and we're doing the derivative. So what does it become? E to the root x over, and it's negative, right? Times what? D dx of what? Root x. You have to remember to do that. You have to remember to do that. So what does this become? E to the root x over root x times a negative times what, Bissell?
1.
Nope. What's the derivative of the square root of x? 1/2 what? To the negative 1/2, exactly. There it is. So the final answer to this is this plus that.
Okay.
The derivative is that, because we did it in two pieces.
Yeah. What?
By this rule we just learned, that could be equal to the integral from -3 to 6 of x squared dx plus the integral from 6 to 4 of x squared dx, right? So let's actually do this out.
It cancels out because it subtracts.
It subtracts the extra bit. You're going to go past
Two
it
steps
and
forward,
then
one step back.
back. You're going to go, no, you're going to go 2 steps beyond it and then come back exactly 2 steps. So when you do this, so look, the way you can prove this without actually doing it out, let's just watch this real quick here. Look, this is equal to the integral from -3 to 4 of x squared dx plus the integral from 4 to 6 of x squared dx. So what did I do? I just took this first one and I split it up like this. You see that, everybody? I just split it up like that. And what can I do to this? If I want to flip the limits of integration, what do I have to do? Minus 4 to 6 of x squared dx. What happens? And you're left with the integral from -3 to 4 of x squared dx. Could we have used a, b, c, and d instead of -3, 4, 5, and 6? You see what's going on there, everybody? So it's really important. The key lessons here, though, when you're using the fundamental theorem of calculus, you have to have a constant down and a lower limit, and you have to have something in terms of x in the upper limit, right? It doesn't have to be called x. It can be called something else. But here's the thing. If this isn't a constant, can you flip it? You can if you need to. Also, if you have no constants, what can you do?
Break it apart.
Pick any constant you want. And what's a great constant to pick? 0. Estimating the area of each of these. So let's say the first one is, this is 2,000, right? Looks like it's really low, right? Looks like it's really, really low. So let's just say 0, okay? So what's the next one look like it's going to be? 4 times what? 1,000. And then the next one looks like it's going to be 4 times what? 7,000? That looks good. And then this one looks like it's going to be 4 times 9,000. And this one looks like it's going to be a little bit more, so maybe what? 4 times what? 1,500? That looks about right. And then this one, let's say it's 4 times what? 250? Is that okay? It's low, right? I mean, are we looking for super accurate estimates here? No. So then what do you do with all these numbers? Add them up. Can somebody just add those up? Now what's the next step? We substitute. So we have the integral of sine of pi t times cosine of, oh wait, we want to use our U-substitution. U times cosine pi t times what? Du over pi cosine pi t. What's the magical thing that happens at this point? Ooh, that goes away, right? And you get 1 over pi times the integral of what? U du. So what's that going to be? That's going to be 1 over pi times 1/2 u squared plus c. And what's the u equal? Sine pi t. So what do you end up with? 1 over pi times, well actually we can do 1 over what? 1 over 2 pi times sine squared of pi t plus c. Did that work out nicely? Mm-hmm. Yeah, it worked out very nicely. Worked out very, very, very nicely. What do we have to change? X equals, sorry, u equals 1 minus x. So what do we have to change? The limits, yeah. So what do we now have? 1 to what?
0.
To 0 of f of what?
U
Times negative du, right?
I see.
Yeah, yeah. But now, next step, what do you do with the limits of integration?
You can
Flip them and make the whole thing. So you get this, and then you bring, yes, slow down, Bill. What happens to the negatives? This is equal to the integral from 0 to 1 of f of u du. And guess what? That's equal to the integral of 0 to 1 of f of x dx. Does it matter what we call the variable? No. Is that the same thing?
Yep.
Absolutely. So guys, when you're in a U-substitution section, it's probably going to use a lot of U-substitution. This was the review, so maybe you didn't have to use it, but you only have very few ways to integrate. You can undo the power rule, right? And you have U-substitution. That's it. You have like nothing else. So if I tell you integrate this, assume that it's integrable, That means you are able to integrate it, right?
Unless it doesn't exist.
Unless it doesn't, I'm not going to give you one like that. So this is that's x1. What's our xn? Which is what? 1. If n is really, really, really big, what does this go to? 0. So you're infinitely close to 0, and you're infinitely close to 1.
So,
Right? So this is actually the integral from of dx. Yep, that's it. That's what it is. So if you ever get one of those and it says evaluate this, do you have to use do you have to use the Riemann sum method? You can't use the Riemann sum method. Why?
we don't know height of the 9.
We don't know what the sum of 1 to the 9th plus 2 to the 9th plus 3 to the 9th plus... Probably not something you're going to want to deal with. I mean, at a minimum, you're going to have to multiply it out and hope everything cancels. No. You need to recognize what that is, and that's a Riemann sum for the sum of the integral from 0 to 1 of x. What's sine of 2 pi? What's cosine of 2 pi? What do you end up with? All done. All done. What did we apply here? You needed, this is a little tricky. I think the hardest part about this is not what we did, but realizing that if you're trying to find f of x, if you're trying to find f of 4, you need to find f of x, correct? To find f of x, you need to get rid of this integral. How do you get rid of an integral? You take the derivative, but are we taking the integral from 0 to x? No, we're taking the integral from 0 to x squared. We need to make sure you're plugging in x squared each time, so you need to make sure you keep that into account by placing what on the outside?
X squared.
Because of what rule? The chain rule. The chain rule still applies. The chain rule still applies.
So
Bill, if this was x, it would be f of x squared. This wouldn't be here. But what is that? X squared. Because it's x squared, you're always using the chain rule. Always using the chain rule. If this was x, what's d dx of x? 1. But what's d dx of x squared? 2x, right? If this was x, then you're absolutely right. It would just be f of x squared. It would just be this. But is it x? No. It is x squared.
Then we have to isolate the function.
And then you have to isolate the function. That's it. This is a creative question. This is pretty cool. This is very cool. If good things to review, your homework, everybody. Review chapter 5. The chapter review in the book is great. That's what you did, those problems for homework last night. The questions you're going to get on the test tomorrow are very similar to the ones in your chapter review.
You just wrote Nat.
Is what?
Is Nat. G-N.
Oh, the E-G-R-A, yeah, is great. I'm a tiger now. There's a Frosted Flakes commercial where the tiger goes, "They're great." It's Mego Dongxi.
No, but that would have been great.
Okay.
That was on the record.
Great.
I'm a tiger now.
I'm a tiger now. The problems plus, everybody, have you looked at them before?
Yes, some of them hurt.
This was number 1 in problems plus. Awesome challenge. If you can work your way through some of those, please do. But focus on the chapter review first. That's your homework tonight. Ready for this tomorrow? Huh? Please, please, please be familiar with the things you're supposed to be familiar with. Meaning, I put them in the other, let me see if I can find it here. Here they are right here. Here's what the test is on right here.
There's one problem still. Having to deal with area and things like from year 2. Or maybe it's 4.
I don't know.
What? Aye.
Oh, no. Sometimes it jumps to the top after pasting. And it really freaks people out, including me. And it jumped to the top for no reason.
Okay, select the whole thing.
Oh, the whole thing.
Dear. You broke it.
Oh, wait, hold on. No, there we go. That's what I just did. Ready? So we're going to take this, copy. Okay. Go to here. Let's see if it explodes.
Yes.
Yay! Areas and distances, definite integral, the fundamental theorem of calculus. Everybody, please make sure the best thing you can do for the fundamental theorem of calculus, memorize it. There's 2 parts. Indefinite integral, net change. Indefinite integral, you end up with a function, not a number. Substitution rule. And what did I cross off here? This. Absolutely. Yeah. Yeah? And. Actually, you know what? I can actually, since that's text, I should be able to. Voila! Magic. Okay. That's your homework. Bell's going to ring in 2 seconds. What?
Is it almost break? Yep. And then very unhealthy amounts of food.
What?
I said almost. That's almost break.
Oh, almost break.
And then very unhealthy amounts of food.
See you, Powers. See you, Bessel. See everybody. Did you go see the Twilight movie, Killian?
I did.
Of course you did. Get out of here. Leave now. I'm going to see it too at some point. So.
It's hilarious.
It really?
I found it really funny. I don't know why, but I was laughing the whole time.
Really?
Yep.
It's just like absurd?
It is. It's so weird and disgusting at some point.
Really?
Yeah. You should see it.
Of course. I have to be able to articulately destroy it.
Yeah.
See ya. How you doing, Josh?
I'm doing well. I've been told you need to fill this out even though I'm only leaving your class very late.
Might as well.
I will be departing at 1 o'clock for a 1:30 departure. I've been told I need to be at the bus at 1:15,
Yeah.
so I got to get to
Get
the
your
door.
stuff. Pick up your bags. Yeah.
Exactly.
Good luck.
I'll be here, this is tomorrow, of course. I'll be
No,
here.
I know. Just good luck managing it all.
Thanks. How did your weekend go?
It's good.
Your cold disappear?
Yeah. Went up to Montreal with kids on Saturday. That was pretty fun.
I had some fun this weekend. I told you about that company that synchronizes all the different cloud services.
Yeah.
So we were trying to figure out why, when you put something in the folder, it automatically shares it. But you don't have to go into and share each file individually. For some reason, the API that they are using, it doesn't tell them the file exists until I actually open it in Gmail, even though they can see from their end that it was put there. For example, it was put on the 18th. I tried to figure out when it got in my Dropbox on the 20th. I called them up, and they're like, well, we do different things. I opened it up in Gmail, just in Google Docs, make sure it's there, and then all of a sudden it's synchronized.
sure.
So they're trying to figure out on their end why. It's the strangest thing.
Go to class.
I've got a free block.
Oh,
but
cool.
I will see you.
See you
Block.
shortly. Yeah.
You want me to take those keys back to Mr. Willie?
No, I gotta do some more paperwork. Thanks.
See ya.
Yeah.
That was interesting.
I think I might have did it.
Why is my bag so light today? Don't know
Got
where.
rid of those books.
Did they really weigh that much?
Yeah, they did.
Because it feels like
I
5 pounds later.
I left them out of my bag. And it
it was so much later, and I feel my backpack now. Exactly. I'm like, what am I missing? And we forgot like everything, but I haven't missed anything yet.
No, in basketball there's varsity JV freshman. Kind of like in soccer, and we called ours JVB.
No, because some of the freshmen are on JVA. Some of the freshmen are on JVA.
I know.
So it's not all freshmen.
I didn't say that. I said,
But you called the freshmen JVB.
no. Freshman is for freshmen. You said, so freshmen can still make JVA and varsity.
I would assume so.
Well, that's still doesn't
It was pretty
explain.
easy.
Yeah.
How'd the rest of the other play go?
Where'd my
Last
table
one?
go?
Yeah.
Yeah.
That's what I meant.
Oh, it was great.
You did good. You did good.
Is there a cast part?
It was long.
Oh, yeah.
Yeah, it was
I know. The cat's pretty cute.
Really?
I was weird. Everyone
So
just
last
like
time the awards
started